So it's now my great pleasure to introduce Danica Kragic here in this room. And I think she also doesn't need an introduction, but let me give you one anyway. So she's a professor at the Royal Institute of Technology, or better known PTH, in Stockholm, Sweden. She received her Master of Science in Mechanical Engineering from the Technical University of Rijeka, Croatia, and then her PhD from PTH. She has been a visiting researcher here in Colombia and in the Johns Hopkins University and also in INRIA in France. She received the very prestigious IEEE Robotics and Automation Society Early Academic Career Award. And her research generally is in the area of robotics, computer vision, and machine learning. But I would say any robotic manipulation task you thought of, you might have a look at the results of her group, you might find something. And I think this is especially true for robotic grasping, and lately also deformable objects and food preparation. And with this, I would like to welcome her here on our workshop for learning implicit representations.
Thank you so much. Hopefully you can hear me. If you can't, just shout. I also want to praise Dieter for his talk. Always very fantastic and very difficult to come after you, Dieter, you know, be novel and kind of like challenging. So since I knew he was going to come before me and do all the latest work, I started to feel a bit nostalgic and look back. And I actually looked back 10 years, exactly RSS, 9-10 years. What were we publishing then? What kinds of problems we were addressing? So I wanted to go back by talking a little bit about the problems we addressed then, just kind of like pave the ground for a discussion we might have, or you during the day. Are we still addressing the same type of problems? How do we define them, and whether the techniques that we are developing nowadays are actually able to address some of these problems or questions? Now, our kind of work has been in many different areas that where grasping and object manipulation is kind of an integral part of it, filling and emptying shelves, and thinking about the problem from the multimodal kind of perspective, not relying solely on the visual cues, by thinking also about robot positioning, navigation, the ability of robots to use the full body when interacting with the environment. We also look in various types of human-robot interaction tasks where the teaching, tutoring, we have a changing role between the human and the robot. In some applications, robot can serve as a third hand and basically help the human to execute the task. And then they need, of course, lots of knowledge about what the human is supposed to do. Or through interaction, also extract lots of instructional videos and try to understand how to reason and help building systems that can reason together with humans. I would also like to bring up a set of collaborative tasks where compliance and physical interaction then with big and bulky objects is something that I don't think that we are seeing enough of it these days. And I think that some of the models we are developing really that are very focused on specific types of scene and specific objects or specific views of those objects are not so easily transferable as representations, implicit, explicit, when we talk about collaborative tasks such as, for example, this one. So I think what is important is to really make sure that when we talk about grasping physical interaction with objects, we do kind of consider a full range of tasks and applications, so not to corner ourselves as the community and thinking very much about you know, well-structured scenes and stuff like that. And of course, in order to be able to do that, we won't be, I don't believe myself, at least, that we will be able to do everything with a single type of network or hierarchy of reinforcement learning algorithms and so on. I still think that we will need to resort to some form of good old planning, especially with a human in the loop. And the reason for this is that there will be just so many unexpected things kind of like going on, and so many untrained users that robots will be interacting with, so that we will definitely need a rich set of representations to deal with problems like this. Now, I think that all of us would like to see robots doing, well, all of these or some of these. And I think it's still fantastic that we all have something to do as researchers, because I would say that if we consider open-ended environments, most of the algorithms or methods or approaches that we are developing these days can hardly get robots to address or demonstrate some of these problems. And it's not so much about being able to, just shred fruits or vegetables, or tie a shoe, or potentially at some point change a diaper. But it's about really how do we transfer the models between many of these different tasks, and how do we also do this by considering either that we have some knowledge of the physical parameters, where by physical parameters I mean something like friction coefficients and so on, or are these things something that the robot is actually capable of learning. And despite the fact that we do have some attempts of extracting friction from just videos and things like that, I still think that there is a long way to go. And in really, let's say, in open-ended environments, put this into the context of interaction with deformable objects, and again, changing media in which the interaction is happening. So if we talk about water or oil and so on, and try to understand whether some of these implicit representations now that we have, continuous representations, can actually help us to understand better of how to transfer or learn representations that are relevant for such pretty, I would say, complex dynamics that some of these actions exhibit. Now, again, I just want to also go a little bit back to what I see is still happening, or well, happening in the community when it comes to the grasping and interaction. I think grasping has been or become very much as a tool for doing many other things. But there is a big difference between grasping and manipulating objects. And I think that picking up something, I think that for most of us, especially if the object is rather simple in geometry, and we consider only a parallel jaw gripper, maybe we can say that that problem in one way or another is solved. But we do talk about robots solving various types of tasks. So they will be picking up something, not just for placing it somewhere or rearranging maybe the scene, but there will be an action that in some cases will require skillful manipulation. And by skillful manipulation, I mean tasks such as, picking up a key and putting it into a keyhole, where I think it will be extremely difficult to learn end-to-end compositionally tasks that do not consider contact-rich manipulation with those that do, and have the representation that actually can scale over all those different kind of requirements. And just to give you a couple of examples, so let's say that we all now just decide to work with parallel jaw grippers. We can consider robots that have two arms. Sooner or later, you will need to reorient something in your hand, or well, robot will need to reorient something in its hand. Why? Because many of the skilled manipulation tasks will require that post-action in a way that requires a changed pose, or that requires that the grasp can counterpart in a way the external forces that will be applied on the object once it is grasped. This example, I've been showing it again for the 10 years, so bear with me, it's a 10-year kind of like nostalgic presentation. I still think that this is fantastic, that the hands are just tools for manipulating tools that we humans use, both low-level information in terms of adapting if something starts to slip, but also there are things such as velocity. So how fast we interact with objects, if it is, for example, a blade of a knife, or it is a porcelain bowl or something like that, something covered with oil. We somehow have that representation of how friction coefficients, for example, change and adapt to it, so that the object doesn't break, or that it's not slip from the hand or something like that. Apart from that, we have the skillful dual arm manipulation. Also, very few works that we are seeing these days are about dual arm. I don't know why, maybe it's very difficult, but I think it's definitely very helpful to consider that there is a second hand that can help with reorientation, or potentially stabilize a grasp or something like that. And then, of course, I think we also kind of went away a little bit from more than two fingers or just a parallel jaw gripper, and from also equipping the hands with the necessary tactile feedback. I think that many of the tasks robots will continue or will need to do will require some of these finger gating, because if the robot is to interact with a deformable or soft object, to counterpart some of these external disturbances, well, two fingers can continue to hold the object. The third one will need to move in order to generate a more stable grasp, and so on. So how do we do this? I mean, this kind of like control, where even now this external kind of like disturbance may come from a human doing this, as you just saw it. It might come actually from collision with the environment and so on. So taking this into account without any visual feedback while you're doing this, I think it's going to be very, very difficult. So my point being that many of the models we are seeing today are still kind of, apart from maybe integrating vision and language, I would like to see more of this kind of force torque tactile integration, and see how the models that we are using today can actually adapt to both doing this in a real-time setting, but also encode both the redundant information that comes from maybe force torque in the wrist and tactile sensing, plus, of course, the vision. And again, I think that we also need to think that there are ways of solving many of these things with, of course, reinforcement learning, end-to-end thinking, and so on. But I think that there has been so much work in the classical control community that can solve some of these problems when it comes to actual in-hand stability or rearrangement and so on in a much better way. So one of the challenges, I think, for us also when it comes to implicit representations is how do we deal with the state representation, right? So what is being represented so that it can be used for tasks such as we have seen also in the previous presentation, task relevant grasping and so on, but also something that can be used as an input to rather simple controllers that can then maintain stability of the grasped object and so on. So I think that that's also one of the relevant problems to continue to look into. Now, when we talk about scenes and data in general, again, this is a point cloud that has been generated with a set of stereo cameras and reconstructed. Nobody uses this anymore. Again, video is like more than 10 years old. So I think that there still remains for all of us to kind of like address the problem, what is an object? So do we really have a good understanding of the object and whether the embeddings that we kind of like develop and the representations we are using really have this notion of the object. And I know that right now there is a kind of like a religious moment maybe in the community of drawing this parallel to the human. Well, we humans don't have that. We have some canonical representation, and that's basically enough. But sooner or later, some metrics needs to come in, right? Because we are acting in the physical world. So even with implicit representations, I think we will need to think about how that metrics is encoded in the relevant way. So it doesn't matter if you are Alice in the Wonderland and have like huge cups in front of you that you can't manipulate, or have cups of the size that you can manipulate. I think that this is very relevant. And there has been quite some work, if you look into the work that has been done on encoding foveal and peripheral vision. So this was just one example with an active robot head, where we actually used cameras with small and large field of view in order to then have representations that are relevant for the robot to approach an object, but then a high resolution images that allowed us to reason something about where to actually move the fingers once the grasp has been applied to the object. And why is this relevant? Well, I think that any video of grasping that you can look at, the grasp you plan will very seldom be a grasp that you ended up with. And I'm just a little bit kind of still wondering why nobody talks about that. So you do generate that red point that Dieter has shown. You send your arm to that X, Y, and Z position, potentially with some orientation. But then you do have maybe a little bit of an offset, or the fingers do not close with the same velocity, or whatever problem you might have. The object might rotate at the end. So the executed grasp will have or will be different from what you actually planned. And in most cases, given small fingers and bulky objects and so on, it will be successful. But these are the measures that we are using today to say whether it was successful. So we are not measuring whether we actually executed the grasp we planned. We just measure whether by some chance we had such a luck that the relevant maybe sizing of the object and the hand is such so that the embodiment itself can compensate for some of those errors that we actually never report. So when I look back again, 10 years, I mean, we thought that that was a big problem, especially when you work with multi-fingered hands and when you want to generate multi-fingered grasps, right? Because then, especially if you assume rather complex geometries of objects, it actually does matter if your fingers do not end up where you planned them to be. So lots of the work that we did at that time was about integrating then visual and tactile feedback in order to be able to understand from then the tactile readings whether the grasp has a success, certain success value or not. So whether it will succeed given then tactile feedback. I can talk about this for quite some time, but we don't have time. So what I think is really, really important is to actually, once we start to deal with tasks that are not only dropping the object somewhere, but really using a key to put it in a keyhole and things like that, we will really need to understand where the fingers ended up to be. And I think that for that, either the robot will need to have a set of kind of like strategies for looking into the things, or we will need to have some form of a real-time tracking of objects to really understand then the relation between the fingers and the object. And I still think that tactile feedback can be very helpful, if not more just for kind of like classification of or looking into the probability of a certain grasp being stable or not. Let me skip a little bit over that, examples that I have right now. This relate very much to the fact how did we deal with task-oriented grasping quite some time ago, how we transferred grasp between humans and various types of hands, so how one has done embodiment transfer. I'm not going to talk about this very much because I think it's very little work being done on this, so maybe nobody's any more interested. But what I think is important is how then implicit representation, so having some form of a continuous reasoning over various types of categories of objects and relations to the task. So can we understand, or can we, if you now think about these spheres being the distributions of good or bad grasps that are conditioned on the task? So something like handing over an object, or pouring, or dishwashing, and so on, trying to understand whether we can attach to object categories, or in some cases we will need to go to instances, of course, and what types of grasps are relevant and how these relate to the task. And I think that this will continue to be an important problem, especially again when it comes to a little bit more complex tasks than just dropping something at a certain point. And yes, I do believe in simulation. We have been using simulation for a really long time, and what I'm looking into is that we didn't have it before, so we developed our own long time ago a simulator that can simulate tactile feedback. I would like to see more of that, so that the data that we are using in terms of successful or unsuccessful grasps are not only related to the pose with respect to the object, but also have some tactile feedback and potentially more information also that is related to, let's say, local geometry with concave objects and stuff like that. And another thing that I think is also very important, and that relates to many of the things that Dieter has been talking about, is understanding this rather complex objects configurations. And I think that even if we think about categories of objects where if these are learned or not, if these are easily kind of segmented by being single colored and so on, in most cases we will have a problems of resolving the scenes by really understanding whether it's a single object or a composite. So let's say that you have an object that is kind of like three glued cubes on each other, and understanding that. So can the network that has learned that a cube is green generate then, and how can it perform in the environment where somebody has glued two cubes together and so on. So I think that this comes to mind when one deals with real objects that have texture, that have lids, bottles with caps and things like that. And yes, I do believe that the recent advances have helped us a lot to retrieve some of the information from human grasping. We continue to do this. Now, this is rather novel work, but understanding how from instructional videos we can extract information that has to do not only with how humans grasp and where the fingers are put, how this is related to the task or to the way the object is used and manipulated, but that also we can understand better of how we can then transfer this to various types of kinematics for hands that are not only two-fingered hands and so on. And there are a couple of recent works that we have done on understanding or extracting this information from human activity data sets. I think that my time is out, but what I think that comes back now to my mind, again, almost 10 years old work, and that very much resonates with all the implicit representations that we are talking about, are grasp moduli spaces. So very long time ago, we had an idea that it would be really, really nice if we have some form of a continuous representation that can continuously deform between different types of object shapes. But not only that, have some form of a common representation that together with the shape molding in a way molds also the grasps, or in this particular case, stable grasps. So if you now consider here that we move from something that looks like a book to something that looks like a bottle through some continuous representational space, we would not only like to find then how then to generate this shape change, but also how these three vectors here that are corresponding to a three-fingered grasp would move, given then and respecting the potential kinematics of the hand, to keep the stable grasp on the object. So if there is one work I would like everybody who is interested in kind of like continuous representations to actually address, would be something like this. So this is just a quote from our own paper. We do not think of a collection shapes in a discrete manner, but instead take a step towards understanding grasp on families of shapes varying continuously. And how we can, in a way, change the grasp by varying different types of style parameters, and then also study this theoretically. So can we understand this kind of like underlying space, and by having a representation on which we can for which we can understand what it does in terms of, for example, what types of objects it can represent, or object geometries, but also at the same time, how can we study grasp stability. So for those that are interested and maybe want to find this kind of relation between the grasp moduli spaces and nerves and everything that has been developed during the past couple of years, I think that this would be one of the works I would definitely suggest. So how can we then show the evolution of stable grasp under small deformations on objects, thinking about randomized grasping and so on. But also, how can we formulate a grasp quality gradient approach on whatever representation we have, hopefully continuous, so that we can transfer stable grasp from one surface to another surface, evaluate this in both simulation and, of course, demonstrate in the real world. So when it comes to large data sets, yes, we were able to, with methods like this, do 100 million grasps already 2013. So I think that we can definitely find ways of how the underlying mathematics can help us to address large-scale problems. But then we also at the same time need to be able to understand the properties of these spaces that we are kind of like learning, and how these are suitable for various types of tasks. I think that I will probably stop here. And again, for those that are interested, there was a continuation of this work. We are currently looking into, again, the models that we can use in order to address rather simple, similar types of problems as we did before. So how can we, in connection to various types of representations, look into how randomized grasping can also help us to find locally more stable grasps by also controlling the hands that have more than two fingers, and that also kind of like where the kinematics is taken into account. So I think I'm going to stop here, because I know that we should have a little bit time for a discussion. So I don't have too much to say about cutting and deformable objects, because I know that recent work everybody reads. I strongly believe that many of the tasks I'm demonstrating here are going to need various types of implicit representations, but again, how to actually put those together with maybe model predictive control or something like that is still for many of us in the community to kind of like see. So I'll stop sharing here to give everybody time to, ask us questions, both me and Dieter maybe this time. Thank you.
Thank you so much for this great talk. So we do have time for one quick question, and then we go to the discussion session. Anyone have a question, the audience? Then I have a question. So the work you last showed about the grasp moduli spaces, you said that these were analytical functions, or were they learned? And
they were analytical functions. So that's why I said I think it is important to kind of like see you know, how the learned versus defined can potentially, you know, when do we need the other, one or the other? And I think that what we are seeing, even with the learned ones, is that we have very similar challenges as we had with kind of defined ones with analytic functions, right? Is that the objects are rather smooth surfaces and things like that. And where we have problems when it comes to grasping is really when we want to represent kind of like, you know, small concavities and things like that. And that's why I'm kind of wondering whether even with the new representations, yeah, maybe we can do more, which still stands to say. I'm not so sure. But how do we actually address the problem of uneven geometry?
Thank you so much. Let's thank Danica again.